Hello, Year 10, or should I say Year 11, as you are now. Welcome to your second week's worth of science lessons. This is going to be focused on chemistry this week. Now, this video lesson is predominantly for those people that haven't been able to make it into school for your chemistry lesson this week, or for those of you that have been in school and would like to see the lesson again. This is the exact same lesson that the people who have been in school will be getting as well. Now, your chemistry, we are going to be moving on to a new topic. It's C9, which is all about chemistry of the atmosphere. And this lesson today serves as the introduction to that topic. It's all about the origin and the evolution of the atmosphere. And it will lead into what you will be continuing doing when you return to school in September. Now, by the end of this lesson, you should be able to do these three things. You should know the composition of the atmosphere today and on the early Earth. You should be able to describe how the atmosphere has evolved over the last 4.6 billion years, and you should be able to interpret evidence for this evolution. Now, before we go any further, can you just make sure that you've got a pen, a piece of paper? You shouldn't need a pencil, but it might be worth having a different coloured pen. I'm going to give you lots of different tasks throughout the lesson, throughout the video, and at each task I will ask you to pause it, so you get an opportunity to write down your answers, and then I will tell you the answers, and I'd like you to self-mark and correct in your different coloured pen. This is so that when you submit your work, your teacher can see that you have been completing each task. Okay, let's make a start then. So your starter task for today is, can you write down any gases that are found in the Earth's atmosphere? And as an extension, can you write down what percentage of the atmosphere these gases actually make up? So pause the video now and have a go doing that for me, please. Okay, let's see what you've got. So there's a pie chart which tells you the composition of the atmosphere as it is today. And you can see that nitrogen makes up 78% of the atmosphere. Oxygen makes up 21% of the atmosphere. You've got argon, which makes up nearly 1% of the atmosphere. Carbon dioxide makes up 0.04%. And then you've got other gases making up less than 1%. Okay, so I've got a question that we're going to hopefully answer by the end of this lesson. Has the Earth always had an oxygen-rich atmosphere? So let's start investigating this. What is the atmosphere? So the atmosphere is a thin layer of gas that surrounds the Earth. The Earth is the only planet in the solar system which has an atmosphere that can sustain life, and it does this in a few ways. First of all, it protects all life on Earth by blocking out the harmful ultraviolet radiation from the sun. So the radiation that causes your skin to burn on a hot day, the atmosphere actually blocks out the majority of that radiation that is coming from the sun. The second thing that the atmosphere does, it actually keeps us warm. So without an atmosphere, the average global temperature of the Earth would be a chilly minus 18 degrees C, which is roughly the temperature inside your freezer at home. However, because we've got an atmosphere, the average temperature on the Earth is 15 degrees C, which, just think of a nice warm spring day. It's that kind of temperature. That's the average temperature across the whole of the Earth. Now, the atmosphere is actually quite thick. It's 480 kilometres thick, but most of it is actually contained within the closest 16 kilometres to the Earth's surface. So the atmosphere does thin as you go out into outer space. Now, one of the important gases that the atmosphere has got, which helps it sustain life, is that it's got oxygen. And oxygen, obviously, we need and other organisms need for respiration. So what is the atmosphere made up of? We did this as our starter. So for the last 200 million years, these gases that we find today have been pretty much the same. Roughly 80% nitrogen, 20% oxygen. And then you've got the few other gases as well. So you've got your carbon dioxide, you've got your water, and you've got your noble gases. So argon, as I've already mentioned, but also any other gases that you might find in group 0 of your periodic table. So for example, helium and neon as well. There's traces of those in our atmosphere. So first little task for me today then. Can you tell me, look at the bar chart and tell me what gas A is and what gas B is? Pause the video and have a go at doing this for me now. Okay, so gas A is 78%. If you look at the bar chart, so gas A is going to be nitrogen. Gas B, it comes up to about 21%, so gas B is oxygen. Okay, second task then. So have a read through this and complete this task for me now. Pause the video, thank you. Okay, so complete that table to show the percentage gas of oxygen. Just said, and we're just seeing from the bar chart previous that it's 21%. However, if you were to write down 20% on your exam paper, you would still get the mark. Same thing goes for nitrogen. It says 78% there, but you would be allowed to put 80% and you would still get the mark. Right, name one gas that would be included in the other proportion of gases. So we could have had carbon dioxide, argon, water vapour, or any of those other noble gases. So where did the atmosphere originally come from? Well, when the Earth formed 4.6 billion years ago, it was just a ball of molten rock. The young Earth was so hot that the atmosphere could not form. It was that hot that any gases were simply just driven off by the heat. Now eventually Earth's crust cooled enough for a crust to form, so you get the land that we get today, but this also allowed an atmosphere to form as well. So where does that atmosphere, the original atmosphere, actually come from? Well, you need to be aware of the volcanic origin of the atmosphere. So there's intense volcanism for about 1 billion years after the Earth was formed, and this spewed out huge volumes of gases from the Earth's crust. Now, the force of gravity actually allowed these gases to actually remain close to the Earth. So they are held in place and gradually an atmosphere formed around the Earth. So the origin of all the gases that were in the original atmosphere were from volcanoes. But how do we know what those gases actually were? So how do we find this out? So we need to look for some evidence. So we can look for evidence in two places. We could look for evidence on Earth, and we could also look for evidence further away from the Earth as well. So what I'd like you to do now, if you were in school, I'd be asking you to have a discussion with the person next to you. But I want you to quickly jot down some notes as to where we could look for evidence for the origin of the atmosphere. Do this for me now, please. Okay, so just keep hold of your thoughts. Now, one of the ways that we get evidence for the origins, what the gases in the early atmosphere was like, was from volcanoes. So gases released by volcanoes today should be very similar to those produced by volcanoes billions of years ago. So by looking at what gases are being spewed out of volcanoes today, we could make an educated guess as to what gases were being spewed out billions of years ago. So it gives us a bit of evidence. By looking at the gases today, we could say, well, perhaps the early atmosphere was made up of those gases. The other place we can look for evidence is on other planets. So we've got atmospheres on Venus and Mars, and there's no life on these planets. So these give us a good idea of what an atmosphere on Earth would look like if there wasn't life present. So we could look for evidence and see what gases are present on Venus and Mars today, and that might suggest what the Earth's early atmosphere was like as well. So what was it like? So 4.6 billion years ago, it was very different because we had lots of volcanoes, no life. So we kind of think that there was methane, carbon dioxide, water vapour and ammonia. They were the main gases present in the Earth's early atmosphere, but the majority of the gases was carbon dioxide. Now this slide says 70%. Scientists aren't particularly they can't agree on exactly what percentage of carbon dioxide made up the original atmosphere, so you might see varying from 35% all the way up to 95%. But the majority of the Earth's early atmosphere was carbon dioxide. So look at these pie charts here. So we've got a pie chart saying what the gases of the what the Earth's early atmosphere was made up of, and what the atmosphere of today is made up of. Now, for your third task, I'd like you to tell me how the amount of carbon dioxide, nitrogen, and oxygen has changed over time. So pause the video and try and tell me this now, please. Okay, so let's see what you've put. So there has been an increase in the amount of nitrogen and oxygen in the atmosphere, and there has been a decrease in the amount of carbon dioxide in the atmosphere. So that's important. We've increased the amount of nitrogen and oxygen, and we decrease the amount of carbon dioxide. So you should have been given a little resource pack as well, and in that resource pack there was an exam question. Now I'd like you to try and complete parts A and B of this exam question now for me. So pause the video, find that exam question, and complete parts A and B of that for me now, please. Okay, so part A. Use the names of gases in the table to complete the sentences. In the Earth's atmosphere today, the main gas is nitrogen. And then in the Earth's atmosphere billions of years ago, the main gas was carbon dioxide. Scientists do not know the accurate composition of the Earth's early atmosphere. Suggest why? Well, scientists don't know it because humans had not evolved then, and it was a very, very long time ago. Use information from the table to answer this question. Water vapour is present in the atmosphere of the Earth and Venus today. The Earth's surface is mainly covered in water. Suggests why there is no water on the surface of Venus. It's because it is too hot. The temperature is above 100 degrees C, so water would evaporate. Okay, next task for me then. So I would like you to sort these statements into early atmosphere and current atmosphere. Pause the video and try and sort these out for me now, please. Okay, so starting over here in the top left, so mostly carbon dioxide, you should have put that that is the early atmosphere. Roughly 1% argon, so just going below it, that is the current atmosphere. Less than 0.1% carbon dioxide, that is the current atmosphere as well. Lots of methane, that is the early atmosphere. About 20% oxygen, that is the current atmosphere. Very little or no oxygen, that is the early atmosphere. Mostly nitrogen, that is the current atmosphere. Lots of ammonia, that is the early atmosphere, and lots of water vapour is also the early atmosphere. Okay, so that should have completed our first objective, which was to describe the composition of the early atmosphere and also the composition of the atmosphere as it is today. Now we're going to move on to our second objective, which is to make an explanation for that change. Now to do this, we need to form ourselves a hypothesis. Now a hypothesis is a possible explanation for a scientific observation. So we've got our scientific observation. There is a change in the amount of gases, different gases in the atmosphere. We now need an explanation for this. So to do this, we need to think about how this may have changed. So what I'd like you to do, I'm going to give you 30 seconds to write down what may have caused that decrease in carbon dioxide and what may have caused that increase in oxygen. Now as a little clue, you need to think about stuff that you've done in your biology, particularly the stuff on bioenergetics, which is B4. So have a go for 30 seconds, write down something that might be occurring that will have caused a decrease in carbon dioxide and an increase in oxygen. Okay, you're going to keep that written down and you're going to see if you're right as we go through the lesson. So let's have a look at some changes. So we're going to look at the change in nitrogen to begin with. So the amount of nitrogen in the atmosphere has increased. So what has caused this? Well, as we've already talked about, the prominent theory for the origin of the atmosphere is through volcanic activity, and volcanoes spew out water, carbon dioxide, ammonia, hydrogen, helium, methane and nitrogen gas. So the nitrogen gas there is quite important. So because volcanoes produce nitrogen gas, nitrogen is actually quite inert. It's not very reactive. And so because it's not very reactive, it can gradually build up in the atmosphere. So as volcanoes are spewing out more nitrogen gas, that nitrogen gas can just gradually build up in the atmosphere. Now there is another source of nitrogen, and if you look at this picture, you can see that our ammonia here contains nitrogen. It's got a capital N there in the molecule. Now, as the amount of oxygen increased in the atmosphere, the ammonia reacts with the oxygen, and that can form nitrogen gas as well. So because volcanoes produce ammonia, they can also cause an increase in the amount of nitrogen gas. Now, the next little key step in the story of how the atmosphere developed is the formation of the oceans, and it's quite an important step, this is. Now, during the first billion years of the Earth's existence, we've got our volcanic activity, and it's mainly, the two main gases coming out of the volcanoes are carbon dioxide and water. Now, as the Earth cooled down, water vapor in the atmosphere can condense. So little water droplets can form in the atmosphere. It can then fall to the surface of the Earth as rain, and this in turn eventually formed the oceans because there was so much water vapor in the early atmosphere. Now this is really important, but let's just have a little check of what you can remember from the last two slides. So what were the main gases in the Earth's early atmosphere? And why was there no liquid water on the Earth to start with? And why did the oceans form? Have a go at answering these three questions for me now, please. Okay, so the main gases in the Earth's early atmosphere were carbon dioxide, water vapour, methane and ammonia. Why was there no liquid water on the Earth to start with? It's because it was too hot for water to exist in its liquid state. And why did the oceans form? Well, as the Earth cooled down, water vapour in the atmosphere was able to condense, fall to the Earth as rain, and it formed the oceans. So, how is this important? Now, the formation of the ocean played a really important role in the evolution of the Earth's atmosphere. Two reasons. Number one, it acts as a sink for carbon dioxide, and number two, it provided the environment for life to evolve. So why are these important? Let's have a look at this sink one first. So when oceans form, carbon dioxide can actually dissolve into the water. So carbon dioxide can go into the ocean. Now, as it goes into the ocean, this dissolved carbon dioxide goes through a series of reactions until you get carbonate precipitates that form sediments on the seabed. So precipitates are solid pieces that form in the oceans, and then these will gradually form to the bottom. They just sink to the bottom, and you get lots of sediment forming on the bottom of your seabed. Now, the second reason is we need to look at this picture here. So what is this picture showing? So this picture is actually showing photosynthesis. So when green plants and algae evolved over most of the Earth, they began to absorb carbon dioxide in the atmosphere, and then they started using it in a process called photosynthesis, which you should have met from your biology. So there's a photosynthesis equation. Carbon dioxide plus water gives us glucose and oxygen in the presence of light. Now this is important. You need to be able to write this equation down. You need to at least know the word equation for photosynthesis. So task 6 for me then. Can you have a go at answering these three questions? Pause the video now. So, which of the following may have caused a decrease in the amount of carbon dioxide in the water? It is actually A and B, dissolved in oceans and photosynthesis. Volcanic activity actually increases the amount of carbon dioxide in the atmosphere. Can you complete the equation describing photosynthesis? So we've got carbon dioxide plus water. It gives you glucose and oxygen in the presence of light, and there is the balanced simple equation as well if you wrote that down. And photosynthesis provides oxygen. How might this change the composition of the Earth's atmosphere over time? So we haven't actually talked about the increase in oxygen yet, but if you look, because photosynthesis is increasing the amount of oxygen, the amount of oxygen found in the atmosphere would gradually increase over time the more plants there are to perform photosynthesis. So, increasing the amount of oxygen, algae first started producing oxygen about 2.7 billion years ago, and then over the next billion years plants evolved. The percentage of oxygen gradually increased to a level which enabled animals to evolve as well. Okay, so we've seen how the levels of carbon dioxide in the atmosphere can be reduced by dissolving it in the oceans and also through photosynthesis. However, to get them to such low levels that they are today, so remember, carbon dioxide is going from a really high amount, so 95% it says on that pie chart there, all the way down to 0.04%. There must be other things happening as well, other than just dissolving in the oceans and through photosynthesis. So actually, carbon from the early atmosphere is being locked away in things such as limestones and fossil fuels. So, what is a limestone? Well, if you were to dig underneath Meaden's School, you would get to this rock called magnesium limestone. Now, this rock is actually culturally important both locally and nationally. So it was used to build most churches in the local area, including the Minster Church at Southwell. But it was also used as the foundation stone for the Houses of Parliament. So these stones right at the bottom there actually is this stone, this limestone, which came from a quarry in Mansfield Woodhouse just down the road. But why is limestone important in the evolution of the atmosphere? Well, when carbonates form after carbon dioxide is dissolved in the ocean water, they are precipitated out, they produce these sediments. Also, marine animals are using this carbonate to form their shells and skeletons. Now, when they die, the shells and skeletons fall to the bottom of the ocean, along with these sediments, and they are gradually crushed, okay, and they are turned into limestone, which is a sedimentary rock, okay. So there's an example of limestone, and there's a limestone outcrop of rocks, and that is actually the White Cliffs of Dover. That is all a form of limestone. So a lot of the carbon dioxide in the early atmosphere has been turned into this rock, and it's taken away, okay, and it's become part of the land. So now I'd like you to complete this task. So task 7, what kind of rock is formed from the shells and skeletons of marine organisms? And also, second question, what must happen to the shells and skeletons for them to turn into a rock? Pause the video and have a go at answering this one for me now. Okay, so the kind of rock that is formed from shells and skeletons is limestone. And what must happen to the shells and skeletons to turn into a rock? They must be buried and compressed by sediment. Okay, so limestone is not the only way that carbon can be locked away. Another way is through the formation of fossil fuels. So formation of coal. So plants and trees use carbon dioxide during photosynthesis to build their tissues. And when they die, if they died in swamps and decayed in the absence of oxygen, they can form coal. So we've got lots of coal fields near us. There would have been swamps in the local area looking a little bit like this a few 100 million years ago. the trees will have decayed in the absence of oxygen, and they would have formed coal. So this is another example of carbon dioxide being locked away in the form of carbon into sedimentary rocks. Now, the other fossil fuels are oil and gas. Now, they form in a slightly different way. Instead of being formed from plant material, they are formed from marine animals, and in particular a marine animal or organism called plankton. So crude oil and natural gas form when plankton are buried in mud, and the remains of these plankton are covered in lots more sediment. Now, as they're compressed over millions and millions of years, they turn into oil or gas, and the temperature at which they are compressed determines whether they form oil or whether they form gas. Right, time to go back to our exam question and complete part C for me. So pause the video and have a go at doing this for me now, please. Okay, so any three from these would get you a mark. So used by plants, used by photosynthesis, dissolved in oceans, used to form shells, skeletons of marine organisms, or locked up as limestones, or locked up as fossil fuels. Next task then for me. So this question resembles a 6-mark question that you might get in your exam paper. So describe and explain how the Earth's early atmosphere has changed. Now, also in your little resource pack, you've got a picture board which might actually help you answer this question. Also, I've got lots of little small questions that I'm going to put up now, which will help you structure your answers so you don't miss anything out. So when you're thinking about writing an answer to this question, think about these things as well. So what gases were there in our atmosphere? Which is the most or least abundant? What are the average percentage values given to each of the main gases? Which ones have increased, decreased since the Earth has begun? Can you identify the current percentage of the Earth's atmospheric gases? And can you explain how each one of these have changed? So this is a 6-mark question. Give yourself 6 to 7 minutes to try and answer this question for me. Pause the video now. Okay, let's see how you've done. So these are a few things that you could have included in your answer. So the very early atmospheric conditions were probably mostly 70% carbon, little oxygen, bit of water vapour, ammonia and methane. As the planet cooled, the water vapour condensed to form the oceans. Plants evolved and the carbon dioxide decreased and oxygen increased due to photosynthesis. Ammonia reacted with oxygen and decreased whilst forming nitrogen. Carbon dioxide also dissolved in the oceans and became locked up in sedimentary rocks, that's your limestones. Carbon dioxide also became locked up as fossil fuels. And then your composition of your atmosphere today is 78% nitrogen, 21% oxygen, approximately 1% argon, and then 0.04% carbon dioxide, and the other gases make up less than 1%, and they've been the same for the last 200 million years. Okay, so that completes the second objective, which is the evolution of the atmosphere. The third objective is looking for evidence for this change. So we've already looked at the 3 changes that took place between the Earth's early atmosphere and the atmosphere today. We've seen that oxygen increases, carbon dioxide decreases, nitrogen increases, but how do we know that these changes happen? Now, there is a problem coming up with this theory for how the atmosphere evolved, and that is the large timescales. So, we already mentioned that the Earth's 4.6 billion years ago, but there's not a lot of evidence left for scientists to work out what the atmosphere was originally like. So they get creative and they study different things to try and build up a picture. I'd like you to try and make a quick list of some of the things that scientists could study today to help them work out how the atmosphere has evolved. I've already talked about a couple of these earlier on the lesson, so you should be able to get these. Pause the video and try and answer that for me now, please. Okay, so if you were paying attention, you've seen that scientists can study volcanoes and they can study other planets to help them determine what the early atmosphere was like. However, Today, they're also able to observe other processes to show how the atmosphere is involved. And one of the things that they can look at is rocks. So they can study certain rocks called red beds. Now, these red beds are rocks that contain lots of iron oxide. Now, the iron oxide in these red beds can only form if oxygen was present in our atmosphere. So scientists can date the age of these rocks, and then they can work out when the level of oxygen began to build up in our atmosphere to a point where it would have started to support life or more advanced forms of life. Now, what I'd like you to do is, can you write a word equation describing how iron reacts with oxygen to form iron oxide? Do that for me now, please. So what you should have put is iron plus oxygen gives you, so an arrow, iron oxide. Now, the next bit of evidence that we can look for is from evidence from living things. So some simple organisms, such as the earlier bacteria, don't actually rely on reactions that use oxygen to release energy. Instead, they can use other gases such as carbon dioxide. Now, fossils from these bacteria have been found which are older than fossils of creatures that depend on oxygen. So by looking at your fossil record, where you see the change from predominantly these early bacteria to bacteria that you generally see today that use oxygen, again, you can predict at what time in the Earth's evolution there started to be more oxygen in the atmosphere. So it's just another way that scientists can date when oxygen became more abundant in the atmosphere. So, last little task for me then. So the table below shows percentages of the main gases in the atmosphere of Earth and Mars today. So for each gas in the table, I want you to suggest a reason for the change in the percentage of the gas in the Earth's early atmosphere. So for each of those gases, and then as an extension, can you give me a piece of evidence scientists can use to show that Earth had little oxygen in its early atmosphere? And then B, suggest one way scientists can determine when oxygen became more abundant in our atmosphere. So pause the video and have a go at this last little task for me, please. Okay, so let's go through some answers. So carbon dioxide, decreasing carbon dioxide could have been due to photosynthesis, dissolving in the oceans, formations of limestones or fossil fuels. Increase in nitrogen is due to volcanic activity or volcanoes. Increase in oxygen is due to photosynthesis. So what can scientists study to give a piece of evidence scientists can use to show that the atmosphere had little oxygen in its early atmosphere? So we can study volcanoes, we can study other planets, or we can study fossils of bacteria which use anaerobic respiration. So anaerobic is basically using no oxygen. And then suggest one way scientists can determine when oxygen became more abundant in our atmosphere. Scientists can study the iron oxide red beds found in the rocks, and so they can date these and they can work out when oxygen became more abundant in the atmosphere. Okay, so all your work from today, can you take a picture of it or scan it in, send it to your teacher either via Teams or via email, whichever way you normally send work back to your teacher. There's also a follow-up task which will act as your second lesson for this week, so that will need completing as well by the end of this week. And again, submit that to your teacher on the relevant day. They will let you know when. Anyway, hopefully I'll see some of you back in school in September, and then next week it will be your physics lesson. Okay, bye for now.